In this presentation, we will be talking about how to detect ice on power cables based on basic image texture features as well as very basic classifiers and feature selection techniques. Ice storms cause major power disruptions. So for example, in December 2013, one left more than 300,000 customers in Toronto, Canada without electricity. In December 2002, more than 65% of Duke, North Carolina, 2.2 million customers were left without power for days. Power blackouts are very costly. Ice accretion on power lines, twins, or a combination of both cost 80% of the total damage caused on transmission system failures worldwide from 1991 to 1996. Detection work helps to be prepared and take appropriate preventive actions. Manitoba Hydro has installed ice detection stations consisting of a 3.1 megapixel camera, and the camera is focused on a small conductor section, approximately 6 inches long, near the support insulator to prevent cable sagging. The system at this point generated good responses, such as those 4 images shown there when there is no ice, and then there is no alarm generated by the system. For the cases where there was actually ice on the cables, as we can see in those 3 images, the system continued yielding good results. There were other scenarios where fog was heavily present in the scene and good responses with no alarm were obtained. What we mean with no images with fog in this set is that for this particular image that I'm showing there, is that the good response corresponded to actually a case where there was ice, but the fog made it impossible to see. Other images will not generate an alarm even though there was ice present on the cables, as we can see in those 4 images. In other cases, the system will generate an alarm when in fact there is no ice, as seen in those images. The data set available was fairly small, so it prompted us to use simple techniques for feature extraction, feature selection, and basic classifiers. Difficult scenarios require us to do some pre-processing. So for example, that image presents almost no contrast between the background and the cable. Images with moving cars on the background also yielded some problems for detection. Other images will also contain ice in very concentrated locations, so no ice was detected on those circumstances. Another example where lights on the background cause problems. One way to fix all these problems is to work with the edges of the image, so edge detection was needed. In order to perform this, we use the Canny edge detection technique. Canny requires the selection of 3 parameters: the standard deviation of a Gaussian filter at 2 thresholds. In our case, we're just going to select one threshold, and the other one, the lower one, will be just 40% below that level. We fixed the standard deviation as square root of 2, thus we only needed to select the upper threshold. Let's use one of the problematic images, the one that had some moving cars on the background. If we let MATLAB select those thresholds automatically, these are the values that it found for this image, and as you can see, there's a lot of information that we don't need. We should be only focusing on the cable. If we manually select the threshold to be 0.13, we can see that for this particular image, Canny edge detection can help us a lot. Empirically, we defined those thresholds manually and detected 3 regions based on the global standard deviation of the original images where those threshold values were working the best. So for the image on this example, we can see that the global standard deviation is 41.81, which tells us that we should choose a threshold equal to 0.13 according to the bottom of the table that I'm showing you. We are going to refer as using this table as an empirical method, but we would like to use a support vector regression to detect those parameters automatically. 3 global features to identify the threshold used in Canny will be then the standard deviation, that is of the global image, that measures the contrast, the mean intensity value of the image, the average intensity that is, and the entropy of the image. Statistical uncertainty of gray levels are then computed using the entropy. We will be using also 5-fold cross validation to determine those support vector regression parameters so that we can estimate the threshold automatically. At this point, we're just working with images that contain the edges, and it's time to extract some features from those images. We will be using the gray level co-occurrence matrix, or GLCM, and I will post a link to a video that explains the GLCM. In the co-occurrence matrix, we would like to detect lines such as the one in red and the one in blue corresponding to offsets of 1, 7 and 1, 3, and use metrics such as correlation, which is a measure of linear dependency between two pixels. As we can see, correlations for images with eyes are lower than those without eyes. Correlation in the third image is rather high, indicating that there might not be eyes, but as we can see, there is an accumulation on the left, as indicated by the arrow. We will need to consider these cases. Another metric that can be used is contrast, that measures the amount of local variations. Images with eyes have more local variation than those without eyes, and therefore have higher contrast values, as we can see on the images on the bottom. Another good feature would be to measure the width of the cable as we analyze the cable from left to right. It will lead to the signatures that we see on the bottom plot, where the simple standard deviation of those samples can detect the eyes. Another good feature that can be used is based on the Hough Transform, when we can see that the Hough parameter space we will have higher values on images that do not contain eyes on the cables. The detection of straight lines in the Hough Transform will be limited to angles below 90 degrees and distances as indicated in the diagram. As we can see here, images that contain no eyes will yield parameter Hough spaces with higher values, as straight lines are more prominent when there is no eyes. With images like this, the Hough Transform will mislead us to believe that there is no eyes in that image, when in fact there is accumulated eyes. The solution is to segment the image pixels with intensity values above 80% of the maximum value, as we can see on the image on the right. For feature selection, we consider two approaches: principal component analysis and sequential forward selection. For classifiers, we consider four models: support vector classification, naive Bayes classifier, linear discriminant analysis, and quadratic discriminant analysis. Here we show the results we obtain when using principal component analysis for feature reduction. Note that the empirical method refers to the use of the table to detect edges and Canny edge detection, and on the right, what we have when we detect the parameters on the Canny edge detection using the support vector regression technique. Here are the results obtained when using sequential feature selection instead of PCA. Here is a table showing the comparison between the different techniques used to solve this problem. Based on the limited amount of images, using SVR and SFS were the techniques that outperformed the other methods. Using only 8 selected features and using 25% of the 612 images, the best result was 0.0065, which means that among the 153 testing samples, there was only one image that was misclassified, and not surprisingly was the one that contained a lot of fog. More information can be found on this reference.